Hi, in this video we're looking at Option C M&V methods. In the past everybody used utility bills, but now we have smart meter data, and well, you know, the authorities who went and spent all that money on smart meters, they want to do something with the data, and one of the things they thought they could do is M&V. Why not? Well, we'll go into this later, but basically what this video is we look at doing Option C M&V with utility bills. We look at using interval data, so using an interval data model, also aggregating the data into days and also into weeks. And we compare all three of those in terms of different types of errors. It's actually it's a really good presentation. It's done by myself and by Kevin Warren from the East Coast, Warren Energy Engineering. I think you're going to like it.
Okay, so we're going to kick this off since I know we have limited time today, and I think this is going to be a pretty long one. As I mentioned, welcome everybody to our May webinar on the comparison of Option C methods. We have John Avina, who you all are familiar with, as well as one of our partners, Kevin Warren with Warren Energy Engineering. So welcome to them both, and hopefully you guys enjoy what they have to share. As I mentioned in the past, you guys kind of know how this works if you've been here before. We'll do questions at the end of the presentation, so if you have any questions, you can type them into the chat box and we will circle back. I did mention to John and Kevin, if there's anything that's like, oh, we need to talk about it now, they might stop the presentation, but let's try to keep them till the end and then we'll get through them all, hopefully. So just about our presentation here, we have two presenters today. John Avina, again, you guys are familiar with John, president of Abraxas Energy Consulting, been doing this for a long time, since 1994, done a lot of M&V for large performance contractors, and also managed the software development for Metrics 4 as well as Option C. Also done more than 25 million square feet of building stock doing energy audits and retro commissioning. And then our other presenter, Kevin Warren, a professional engineer. He is the principal and owner of Warren Energy Engineering and previously co-founded KW Engineering. I'm not gonna read the screen because I know you guys can all read, but we're also gonna share these slides at the end. So welcome both to Kevin and John. I appreciate you both being here, and I appreciate everybody taking time out of their day today to hear what they have to say. So that is my talk. I'm gonna pass it off to them and they're gonna take over here. Go ahead.
Okay, this is John. So this is pretty much an outline of what we're going to go over today. So we aren't going to just go over comparing the different methods. Part of what we're going to talk about is why has this come up all of a sudden? And one of the reasons is because the software has emerged recently, the interval data regressions. But there's a lot going on in California, and we wanted to talk about that. We'll also talk about the benefits, the challenges of using interval data for M&V. What is it good for, and what is it maybe not good for, and then uncertainty analysis and why does it matter. You'll see why we're talking about uncertainty analysis a little bit later. And then finally, our data. So first off, Kevin, whenever necessary, please interject. But in California, there are some huge changes going on. But first, before I explain that, I guess I think most of you understand this already. There seems to be different spheres in energy efficiency. One is the ESCO market, and most of you are from the ESCO world. And then the other group is the utility world, I guess you can say. And these are the ones that do these utility programs, often through the PUC, or in Oregon's case, maybe the Oregon Energy Trust. And what's happening in California is we spend, I believe, this could be way wrong, but it's a lot. It's about $1 billion a year in energy efficiency through the utilities and then through all these third-party providers, and also the utilities do it directly. And they have these different programs that will, reach out to different energy using clients and help them to save energy. What's happened in California is the state legislature has decided that they wanted to see Option C M&V happening instead of the way we have been doing it with spreadsheets. They call it NMEC. It's normalized meter energy consumption. Is that right, Kevin?
Yeah, that's right.
Okay, so you're going to hear all these people, or if you talk to utility people, they're all talking about NMEC, even though we've been calling it Option C for decades, but that's what they call it. Anyway, what appears to be happening is they're going to be using interval data, or at least that's it. Actually, everybody's trying to still figure it out. I believe it's starting really soon, like maybe the beginning of 2019. But there's going to be hundreds of millions, I think, of dollars in energy savings that's going to be tracked with Option C for these programs, and all these third-party implementers are still kind of feeling their way through this and deciding how they want to do this. But the initial idea was we're going to use interval data. And so there are these programs that have come out, that do this interval data M&V, the M&V 2.0, and one of them is called OpenEE. And I think they're the ones that are actually going to end up doing a lot of the Option C M&V for these programs. Let's see, what else can I tell you? Go ahead, Kevin. Yes.
I just thought we'd mention, so CalTrack is another term you might hear, where I think that's sort of this process that has been set up to figure out the methods that are going to be used. So it's not really a software, it's more of sort of a set of protocols, I guess you'd say. And it may not all be interval analysis. Some of this may be maybe monthly, but we've got this term in here, this embedded billing analysis, where some of the idea is that these savings will be tracked, using the billing analysis, but sort of in more real time as the programs go on. So some of these programs would have been evaluated with a billing analysis approach by the evaluators, by the Itrons and the DNVGLs of the world eventually, but they're trying to do that more upfront as the programs claim savings. So again, this is mostly a different world from what ESCOs are dealing with most of the time, but yeah, just since there's so much attention and sort of chatter out there, I think the wider world is looking around and seeing if there's, is there anything to learn here?
Okay, and so in California, there's a couple approaches to doing this NMEC or Option C analysis, and one is at the building level, or they call it the site level, which is what you guys do, what the ESCOs often do. But they're also looking at it, doing it at a portfolio, or they call population level, where they would combine all of these buildings together, and then they would, track that. The thing is, I think anyone in the performance contracting world knows that the problem with doing, hundreds of millions of dollars, which means, tens of thousands, if not hundreds of thousands of clients using Option C M&V is, well, what about the non-routine adjustments? And how are they going to deal with this? And people are starting to get a little bit fearful. A lot of these third-party program people are starting to say, I don't know how this is going to work. I don't know. And because this is the big problem. And some folks are saying, well, maybe you don't need to do non-routine adjustments if you do it at the population level. Maybe an equal number of buildings will use more and an equal will use less. And so, you know what, we'll just assume that we don't need to do any. Or what we could do maybe is we'll do a study of a bunch of buildings that have no changes, is that right? I have no real ECMs, and see if they go up or down, and then we'll use that as our sample. And if they have a creep, let's say of 3% this year, then we'll just add that creep to our portfolio or our population. That is what they're talking about doing. At the site level, I think I talked to a couple of these third-party program people, and they want to do it at the site level. And so that means that they're going to be doing these non-routine adjustments by hand, and they're going to have to find them and then model them and put them in. And what this is, if you ask me, what it's opening up is a huge problem where you can game this system because these third-party programs are getting paid per kilowatt hour saved. And the client, the guy who owns the building, they're getting paid per kilowatt hour saved. So it's in the third-party program and client's interest to fudge the numbers to say, oh yes, that's right. We're running 3 shifts now. Yeah, that's right. And so then they can add these big baseline modifications. They can get more savings, and then everybody makes more money. And it's like, if you're willing to be unethical, you can make a lot of money. It's kind of like what happened in 2000 with Enron and PG&E and El Paso Gas when we had this massive energy crisis in California. We're kind of setting ourselves up for the same. And do you have any more on this, Kevin, before we move on?
Well, so I guess on this slide, so we didn't mention, so in terms of doing interval data analysis, there's a couple tools out there that, well, there's more than that, but there's 2 free ones, Universal Translator, and then there's an LBNL online tool that are available later on in the presentation. We'll show you some results from the Universal Translator tool. And we want to talk a little bit about sort of because we've been talking about these utility stuff. So maybe you're saying, well, why do I care? I'm not a utility. And there are some significant differences. To some extent, a large program in California, I mean, at the end of the day, mostly they do care about the aggregated result of, hundreds or thousands maybe of installations, but that's very different than a performance contractor who, you care intensely about this one customer or this one building. So you need results that are, understandable and predictable and reliable at a site level. The other thing is it needs to be something that you can, I think, show easily to a client. A lot of times I've seen, the actual metrics baseline reports being pages in the contract. So if you think about a much more complicated regression analysis that instead of monthly maybe has hundreds of parameters in it, how will you sort of memorialize what that baseline model is? It also, as you go into finer granularity in the model types, would be, I guess, considering how you then track and enter non-routine adjustments. It's one thing to put in, a monthly change due to some factor, but how would that be done if you've now got an hourly model, say? So just pointing out there's some pretty big differences between the sort of the role of M&V for a performance contract and then the role of M&V for a utility program. Yeah, so just really quickly, wanted to mention on this topic that EVO and the IPMVP committee are doing a lot of work around these interval data methods. There's actually a subcommittee on M&V 2.0 that just got merged with the non-routine adjustment subcommittee. Non-routine adjustments has been a topic of concern for IPMVP for a long time because of it's the fact that ESCO contracts need it, and that was sort of the first market for IPMVP, still a major one, and there hasn't been a lot of standardization there, but there's sort of renewed interest in that because of this, all the NMEC discussion. There's also a renewed uncertainty guide that EVO put out, and it deals with option C. But interestingly, we had to basically not complete the chapter on hourly data uncertainty because, well, we seem to understand, I think, as an industry, how to do savings uncertainty for monthly, weekly, and daily. It's honestly still an open research question how well it fits for hourly. So honestly, nobody really knows what the uncertainty is yet in these hourly models, and that was kind of that was frankly a major surprise for me being on that committee. I thought we'd call up a statistician and they would just tell us the answer, but honestly, nobody seems to really know the answer.
Okay, so there's a lot of benefit of using interval. So first, I know we're all attracted to the new thing. At least we often are. At least as long as we know it works, we want to see someone else do it first. But if someone else does it first, then we won't want to try it. And there are some real benefits. I assume once you've got it set up, you can, with where the utility is downloading the data automatically into your system, it pretty much could, I think, could work automatically where you don't have to keep, typing in or importing data and all this stuff. It just runs. That's really nice. Also, you can see savings and losses immediately. What I mean is, if you were a very active, proactive building manager, you could do something like say, well, I want to know, really, they talk about a high chill water set point or a higher one's going to save me energy. I wonder what would happen if I just change it. Here, I'll just change it down to 41 or 40. I want to just see what happens. And you can see it very quickly so that you have feedback. And that's really neat. It's a great tool, I think, for people to tweak buildings with and see how the usage responds. You can also capture changes in energy usage patterns quickly. What I mean by that is with utility bills, which a lot of you use metrics for utility bills, and you have to wait like a couple months, maybe even 3 months before you get bills. And then you can't really notice energy usage patterns until you get several bills, because one bill isn't a pattern. One bill could be random. It just usage is high. I don't know why. But after you get 3 that usage is high, then you might realize, oh, we have a pattern. Something happened. Well, that's like 6 months down the road. So that's what's really nice about interval data is you can identify this pretty darn quickly. As opposed to waiting. And that means you didn't, piss away a lot of money, in not making your savings guarantee. Another thing is you can characterize the types of changes that are happening. And what I mean by that is you can identify, when are these changes happening? Oh, I see, they're using more energy. It's not just, with utility bills, they're using more energy. Well, what we can see here is they're using more energy at nighttime. Oh, okay. So maybe they're not turning things off. Maybe they're running a second shift, something like that. That is useful to know when it's happening or what type of energy usage is it. Is it base load change? It's like we're always using the same amount more, or is it something that's varying with weather? So that is useful. That is great. And I think that, it's something bills can't really give you as well. And then again, you can determine when savings is happening, which might be useful if you have TOU meters. You have anything else on this, Kevin?
Yeah, I guess just, that it'll sort of highlight maybe when a problem is happening. Like as you said, is it a nighttime thing? Is it a Sunday afternoon thing? It's not going to tell you what's happening unless you have, remote EMS access or SkySpark or something like that, but it sort of gives you an idea where to look. And, what we're seeing here with these benefits versus some of the challenges maybe of including it in your contract is that the way I think this is probably going to go is that there's a lot of reasons to be looking at the interval data as part of maybe your sort of continuous commissioning process or sort of ongoing building monitoring. But maybe that winds up, and probably it is a separate process from your basically contractual M&V. There's no reason they have to be the same.
Some challenges, getting access or hooking up your system, your M&V 2.0 system to automatic data, that could be a problem. That certainly could be a problem. Autocorrelation, which we're going to talk about in a minute. One thing on the utility programs that was interesting, I don't know if they've changed their tune, but I remember I went to a meeting a couple of years ago with all these people in California, these utility folks, and they were, I asked the question, what are you going to do with all the meters that won't have a good fit? And someone responded, well, we're not going to do those ones. And so they were just going to, they were only planning on, at least 2 years ago, only, addressing buildings that have good fits to interval data. That was the idea. It's like, the ones that don't have good fits often are the ones that really need help, but that aside. So that is a challenge. And then also the non-routine adjustments, and I already talked about how that was going to cause problems, I guess. But Kevin, you want to explain autocorrelation?
Well, so yeah, it really only matters when you're getting into the statistics and trying to understand uncertainty. And the idea is that you know, in statistics in general, the more points you have, the better, right? If you're trying to measure the height of a table leg, and you keep measuring it, and you've got each one's a random measurement with a bad tape measure, say, you do enough of those, you'll get the right answer, is the idea. But here we're regressing, say, hourly data, but each of those observations is not really independent. The usage at 2 p.m. is not at all random from the usage the hour before. In fact, the single best predictor of the usage at 2 p.m. is the usage at 1 p.m. And the usage at noon is also a pretty good predictor of where it's going to be at 2 o'clock. So it means that some of the a lot of the statistics that are based around what they call, ordinary least squares regression methods, sort of the assumptions don't really work because you have these correlated residuals. And so that basically is the reason why a lot of the uncertainty methods that people have used for other types of billing analysis seem to sort of fall apart when you get to hourly.
So yeah, let me add a little more to this. So I think in super lay terms, the idea of autocorrelation has to do with, look, it's a really sunny, hot day. It takes a few hours for that heat outside to make it inside. So that is the lag, and that is a big contributor to this autocorrelation. It's, just because you can't just say, oh, it's 69 degrees or it's 80 degrees outside, therefore, oh, and it's this time of day, and therefore we're going to use this much. It has to do with, has it been hot earlier, or did the clouds just disappear and now it's 80 degrees? That has something to do with it. Also, autocorrelation also happens with daily data. I'm thinking of a building. I mean, this is an extreme case, a building where they lost the building, or in other words, it got too cold and it took them 2 weeks to bring it up to temperature. I mean, the idea that it was too cold the day before and that affected that next day. And so it's that. So daily also sometimes has this autocorrelation problem. What they do to identify if a building has if there's an autocorrelation problem is they look at, let's see, what is it? I guess it's Kevin, you might have to help me with this. I think they do a graph of let's say, of the actual usage and then the usage from the hour before, and see, is there a correlation between the two of those? Is that right? Or they're looking at the error, the difference between, God dang it, now I can't remember it. Do you remember that?
Yeah, maybe a little too deep in the weeds, but I think you're looking at the residuals. So you're looking at your error term basically and seeing if there's a pattern in that. So if your error term's random, that's what you want. But if your error term looks like a sine wave where it's following the diurnal pattern of a day, it means that you're sort of not quite capturing everything in your basic model.
Good, thanks. Okay, let's move on to the next one. So uncertainty, this is becoming a really big deal, certainly among the utility sphere. I don't know about the ESCO sphere so much, but what we're going to see some models a little bit later, but you have monthly, which we're used to, weekly, daily, and then this hourly. How do you decide which model is best? Do you use the R-squared value, the CVRMSE, the fractional savings uncertainty, which we'll talk about? How do you make that determination? And one other question, Kev, well, before I ask you, Kevin, I talked to one third-party person, and she said, well, you just use the one with the lowest CVRMSE. I mean, that's what ASHRAE says. I don't know, maybe that's the answer. The other part was, why has Evo been putting these uncertainty calculations in the IPMVP when, most of us engineers, we're not really statisticians. We don't really understand this. Our clients don't really understand this. So why has Evo been doing that?
Yeah, I mean, it may be sort of, tilting at windmills, I guess, but, the idea is, even if you don't do it in a rigorous way, Evo's feeling is that, any M&V report has uncertainty in it. And so to just sort of be honest with ourselves and our clients, ideally you would say, look, this is the savings, and that savings is, I'm 90% sure the savings is within this bound. we know that it's not exactly the number that we presented, but you can get an estimate of sort of what the range is. Now, I think the reason people don't do that is, we do tons of M&V, and I don't want to generally try to explain that to my client. And what if it's a big range? Then what kind of contractual fight do you have? So I think there's a lot of reasons why people don't. But that aside, I mean, a reason to look at it from the ESCO's perspective might be, you can predict your likely uncertainty by looking at sort of the goodness of fit of the baseline model. And so, we're looking at doing some things like, building tune-ups and maybe guaranteeing the savings around that, where we're not going to have 35% savings. Maybe we're only looking at 6% savings. If I want to do a billing analysis to prove that, it would be nice to know, am I going to be able to see that in my model, right? How if I've got a really tight model, then I may be in great shape to prove that savings. But if there's high uncertainty in it, then I don't want to face a situation a year down the road where I can't see the savings in the noise.
But that's the ash rate. I thought they tried to dumbify that down for us by just saying, look, it's 2 times the CVRMSE. You got to save more than 2 times CVRMSE. Isn't that right? And so that keeps it simple.
Yeah, actually, I'm not sure about that rule of thumb. I mean, fractional savings uncertainty is something that's the equation is in ASH rate guideline 14. It's just that we don't quite know how to apply that yet for interval methods, for hourly methods.
Let's move on to the next one. All right, so I just made this slide just so you can see this is the kind of stuff that we're looking at when we're doing uncertainty. So just lots of statistics, lots of calculations and all this stuff. Let's move on to the next one. There are some really nice guides out there. I really liked the stuff, I think, by Bonneville Power. That one's really nice. Carrie Cobb, she worked with the guy at the paper on the bottom left, Bill Coran. I have a feeling they work together because the papers are really similar. They have the same pictures in them. And Carrie has been really good at making it more accessible to the layperson and not just for PhDs. If you look at the paper at the bottom left, three of these people are PhDs, so it's tough for us engineers who are smart people but not statisticians to be able to understand PhD talk. So that's what's really nice. This regression for M&V reference guide was done by BPA. No, I think it was done by SBW Consulting. That's right, I think. And no, by BPA. It's done for BPA, and that's really simple. It's really nice. If anything on that? Nope. Okay.
Well, I mean, Evo has an uncertainty guide as well, which is good for
that's right.
monthly analysis at least.
That's right. Good. Okay. So we did some models. Let's take a look at what our next slide is. So we did a couple schools. Here's one. This is a slide from Option C, but it's showing a pretty darn good fit of 983. For an R squared, a CVRMSE is really good. Let's take a look at the next one. So then we broke it up in the weekly. Actually, we started with interval and aggregated to monthly. Okay, so R squared 940, CVRMSE is a little worse, so both of them are a little worse. Let's move on to daily, and again, worse. Now with the daily, what we did was we added a weekday or weekend variable. So this has two independent variables, weekdays or weekends or heating degree days.
So I just want to point you kind of the one advantage of having access to hourly data, AMI data, is that you can decide to roll it up into whatever interval you want. So if you've only got monthly, that's what you've got. But if you've got hourly, it doesn't say you've got to do your regressions based on hourly. Just roll them up to days or weeks or something, and it gives you that flexibility to use the time period that you
right. And if you're doing daily, you can actually identify changes in usage patterns pretty quick. So you don't have to just use interval data to.
But you do need to split them up. I mean, it's an added complexity. Is it? Oops, sorry, John.
No, go ahead. Go ahead.
Well, I was just saying it's added complexity. I mean, if you're doing months, you just have one type of month. They're all months. But for something, and same with weeks probably. Although weeks, you might have for a school, you might have summer weeks and school year weeks. For daily, you're usually having to break it up. There's a couple different ways you can do that. Here, it's like with an indicator for whether it was a weekday or not. You can do also totally separate regressions for weekdays, weekends. You could do separate regressions for summer weekday weekends and school weekday weekends, that kind of thing. But you're generally not going to just sort of throw them into one bucket and just compare it to, say, heating degree days.
Let's move on to the next one. So then we did hourly, and we broke this up into two groups. So one regression for weekends and one for weekdays. They shouldn't be together. Next, and we'll see what all the results. We'll stack them all up in the table in a couple minutes. So we did another school, again, good fit. So these ones didn't use the school days variable. So apparently, because they don't use a school days variable, they run the schools. This is in New York. They run the same whether people are there or not. I guess the lights are on all day. I guess the HVAC's on all day. At least that's what this says. Go ahead.
Well, I think it worked. It may have worked for this case too, because this was a heating-dominated electricity, which kind of unusual. They had very little air conditioning, and so it didn't matter so much that summer was a little bit less because there wasn't a lot of air conditioning anyway.
Good. Okay. So then. Again, weekly, it's a little more scatter, lower R squared. In fact, this one wouldn't have worked for you. Next one. And daily was even worse. Okay, now I think in both of these examples, I know you didn't memorize the numbers, and we'll look at a table and compare them, but this is not going to be always the case. But in both of these cases, it seems that the R squareds got worse as we went to greater intervals, and the CVRMSEs got worse.
I think that will happen, that your tightness of fit to that line is going to get a little worse the more granular you get, but you also have more observations. So when it comes to figuring your uncertainty, sort of scatter a number of observations, they have like balancing effect in some ways.
Good. Yeah. One thing that and these are the graphs for the hourly. Talk about scatter. So that thing that I really like about, I think weekly, weekly is the one I always like the most, but weekly and monthly is, it has a smoothing effect. Let's say you have forklifts in your building and you charge them, but you don't always charge them at the same hour, or whatever. There's so much randomness that happens in a building. And the idea of having longer intervals, it kind of smooths that randomness out. I think that's why you end up with these better fits. So we also did another, a building. I don't know what kind of building it is, but it's also in New York, and it was, relatively, actually not that good of a fit. So I had an R squared of 0.739. There wasn't a lot of cooling dependency at all.
So I believe, my recollection is this is a hospital, so it was very consistent usage.
Good. Thanks, Kevin. Yeah, so then, sorry that the CV got cut off, but we'll see it later. So there's weekly, and then the next one. Yeah, so this was an option C. I think I have a little bug in my in this graph, so I'm going to have to fix that, but because I would think that line should have been through more of the bills than that. But anyway, move on to the next one. Hourly, and wow, and then okay, so let's go on to the next one. I think the next one is a table of results. So let's look at all this. So school one, you can see that the R squareds, yes, they get worse. The CVRMSEs get worse. School two, it's the same, and school three, not the same. So in school three, it actually, R squares got better, and the CVRMSEs got worse. So, okay, then we also did some uncertainty calculations. I was using I really briefly showed you some equations. I used the improved ASHRAE 14 method. So that paper by Bill Coran and those PhDs had pretty much said, these are pretty much kind of equivalent. One's better than the others and all that, but they're kind of all good enough. So I used ASHRAE 14 improved. And I found that, at least for both of these, I didn't do daily, but I did the monthly and weekly, that the uncertainty got better, even as the R squared got worse and the CV got worse. Daily was, I didn't want to put, I could have done it, but I didn't want to make a mistake and put bad results here. So I wasn't willing to do that. So I left it out. So I didn't do the daily. Go ahead, Kevin. You have something on that?
There's a lot more research being done on this, so it's a topic of that everybody's still learning. It seems as if generally uncertainty is going to get a little bit better as you get finer granularity, at least probably down to the daily basis if you split things up right. It's sort of unclear again how much better it gets, and some of the statisticians think it might get significantly better. Some think really it's just not. It's going to sort of flatten out. And just to point out, these uncertainty percentages I think are probably not typical. These are probably just about like best case. This is saying, say for monthly for school one, that we're plus or minus 13% on our savings estimate. That's with a model that is a really nice model, CVR MSE of only 6%, so really nice fit and really high savings.
I had a confidence level of 95% on this. That's what I used.
Yeah. So if your savings were a lot smaller, your uncertainty goes up essentially proportionately. Anyway, just to point out that these uncertainty numbers are probably pretty low, and what you'd see in a lot of cases is probably something quite a bit higher.
Yeah, that's something actually that's worthy of mention. So in that uncertainty calculation, the denominator of the whole thing was your fractional savings. In other words, are you planning on saving 5%? No, 40% or whatever? That number has a huge effect on uncertainty because it's the denominator. That's big.
Yeah, and that's essentially, I mean, it may be a little counterintuitive, but essentially, really your uncertainty is in how well you're modeling the total building usage. So if that's plus or minus 2%, which would be really tight, and you're only projecting 2% savings, then essentially it's not exactly this, but essentially your savings uncertainty is like plus or minus 100%.
Right.
But if your savings gets bigger and bigger, then your uncertainty in your savings gets better.
That totally makes sense.
And I think it's interesting to point out here too that the actual value of the savings are reasonably consistent between the different intervals. Sometimes it goes, school one, it basically kept going, savings kept getting lower with the smaller methods, but it didn't. That wasn't. I think that was just sort of random. It wasn't that same pattern for school two. So it's not like one method is going to give you higher or lower savings. No. These are all, estimates with some uncertainty around them. The last one was, I think, more of a test case where they don't think they really had done a measure here. So we're just seeing
right,
just sort of random drift.
Right. So again, which fit is best? And I think what Kevin said, and Kevin, correct me if I'm wrong, is we can't tell you. I think we can't tell you, or at least the experts, the statisticians with the PhDs will disagree, I think. And so it's up to you.
Well, I would say within the monthly, daily, weekly, probably the sensible thing would be to find the model with the smallest savings uncertainty. At the end of the day, you're banking on savings, and you want to know what your uncertainty is in that.
But that means that you're probably, we don't know what the interval data looks like, but looking at these trends, I mean, I only have 2 points, but 3 times they're all showing the same, that the interval data would have the lowest uncertainty.
Well, probably, it seems like, and there have been some papers, I mean, it seems like weekly is probably a little better than monthly, and daily is probably a little better than weekly. I think it may be that hourly is a little better than daily, but we don't really know yet. So these are just a couple examples. These are actually school one and school two from above, where this is using one of those tools. This is using Universal Translator. There's other ways to do it. There's other softwares. We have an Excel tool that does it. There's the LBL one, but this is sort of what it looks like. So this is the baseline, over a year. You're seeing blue is the weather. So this zooms in on a period of, 3 weeks. So you can see it a little more clearly. And you get, weather along the top, and then the red is your actual hourly, and the sort of pale blue is the model. So, a couple things maybe just to see. You can see it seems to do a reasonably good job. It goes up and down with the blue, goes up and down with the red. It is generally going to somewhat underpredict spikes. Almost any model is going to do that because it's going to come to sort of the average or the typical value. So this building, I think it was kind of an odd electrically heated building, and so I think it's spikier than most, but you can see that the model is doing a pretty poor job of hitting these really high peaks. You can also see, I don't know how well people can see, but right where the sort of the third major hash mark is, the temperature drops, and because of that, the baseline model, the teal sort of comes up and kisses the temperature, because the model thinks, okay, because it got cold, we must be using, again, this electrically heated building, we're going to use a lot more electricity, but the building must have had it locked out, and so in the actual case, nothing happened. So it does give you that, you can see kind of the flaws in the model, but also learn some things about how your building is behaving. So this is showing basically the baseline and the actual, but instead of a time series, it's doing it against temperature. So you can see this sort of hockey stick shape that's typical of a heating dominated building, and the model, the red, is all a little more tightly clustered, which is always going to be the case with the model. You're used to seeing maybe the red would, the model would just be a single line, but you don't have that here. You've got this sort of this cloud, right? Because we're only looking at this in 2 dimensions. We're only looking at it against temperature, but all of the modeled, say, results at whatever temperature you want to pick, 65. Those actually represent values for 65 degrees at 2 a.m. on a Saturday, and 65 degrees at 3 p.m. on a Tuesday, say, which have very different predictions in the model. So that's why you don't have a line. You've got actually like a cloud even for your model.
Kevin, we have a question specifically that I just don't want to wait till the end. What's the modeling software used here?
So this one is using the Universal Translator, which you should be able to find if you Google that. It was developed like 30 years ago, I think, by PG&E originally to look at metering data. The PG&E tool lending library did it. And then maybe, I don't know, 5-10 years ago, they programmed this like regression module into it. So then this is the savings plot for that school. So we had 9 months of post data here. So this is the red is the actual post usage, and then the blue is the adjusted baseline. So this is the baseline model that we developed in the previous slide applied to the actual weather data in the post installation period. So major savings here, because basically this was like a fuel switching project. They ripped out all the electric heating stuff and put in a gas. So there's a really clear, obvious delta. So sort of more of the same, just a second school. Next slide. This one doesn't fit quite as well, particularly if you look over here where we zoomed in, say over on the right. The predicted and the actual are really pretty far apart for a couple of these weeks here, and I think this is partly a limit of the tool, or at least a challenge with it, is figuring out how you can sort of play with the periods in there to separate, say, summer from holidays to school weekdays. And I don't think the LBL tool lets you do that really at all. If you build your own, which I don't really recommend, you can do whatever time periods you want. But I think what we're seeing here is where the model wasn't able to do a clear separation between summer weekdays and school weekdays, and so therefore it's over predicting in the summer when the school is partly shut down. And that's something you could more easily account for probably in a monthly, weekly, or daily model. So then, yeah, this is just the same scatter plot. So you, again, the red is the model, more tightly bounded than the actual, which you'd expect. And then here's the savings. So basically through the winter, you can see where this is going from August through March. So we were getting really big savings through the winter with the removal of that electric heating equipment, but pretty significant savings even in August and September. I don't remember what the other measures were there, but so it gives you a little more granularity into figuring out sort of when your savings are happening or when they aren't. You could also plot the delta here and see what that showed.
So I'm going to speak in June in Santa Clara at AEE West. So AEE, they used to have the EMC, I think it's West Coast or something, and then they used to have the World Energy Engineering Congress. They changed their name. So there's AEE West, and the World Energy Engineering Congress is now AEE World. I am going to be speaking again about this and why the whole California thing and why it's going to be a problem. And I think it could be pretty lively because we're going to have people from OpenEE speaking in the same session, and I'm sure I'll be getting heckled. So it should be kind of fun. OpenEE is the interval data company that the third-party programs are using to do their M&V results. And in the following week, Kevin and I are both speaking with the president or CEO of OpenEE at NASCO in Providence. So that should be a lot of fun also, because instead of being heckled, we're going to be throwing things at each other. So that should be fun. I want to answer a couple questions. Metrics cannot handle hourly data. Option C cannot either. So there's that one. There was a question of, all this stuff, everything we did was linear models. Kevin, is the interval data, that model, is that linear?
Well, it's a combination. The one that we did internally in Excel is basically linear with heating degree days or cooling degree days, and then there's in a typical linear regression you'd have the one offset, right? But with the hourly data, if you're using you basically use hour of the week, and so you essentially have 168 different offsets. So there's 168 hours in the week. So it says you've got this dependence on temperature, and then if you are in hour 112, whatever that is, Tuesday afternoon at 5 p.m., then this is your offset. Universal Translator does a slightly different version of that, where they do the temperature dependence is actually instead of doing heating degree days or cooling degree days, they split up for some reason the temperature into like 5 or 6 pieces, and so they figure where these breakpoints might be, and then they say this is the dependence when we're below 30, and this is dependence when we're between 30 and 45, and then on top of that add in the hour of the week parameter. So that's one of the things that makes it complicated on the uncertainty side, is that you've got more data, but also you're trying to create way more parameters also, and so that part hurts your uncertainty.
There's a question also about, let's see, what if you don't get interval data from your utility? What can you do? And I'm going to give one answer, and I think Kevin will give a different. But mine is, if you've got a big building, and I know the Juan asked this, and Juan does have big buildings, you probably have a good BAS system, and I would think you can just add a point to your BAS. That would be an easy way to handle that. And then you would also make sure you got a good outdoor air temperature sensor as well. Kevin, do you got a good answer for that, or a better one?
Yeah, I mean, in some cases you can get what they call a demarc from the utility, where you can get essentially a pulse output, and then either pull that out to some kind of software, or maybe tie it into to your EMS. So we have a like a monitoring solution that does that. But that's an option if you don't want to install, say, a whole new meter at the entrance.
Oh, there's a question about, okay, so R squared's getting worse, but uncertainty's getting better. What? And so I think, Kevin, what you said was, yeah, we get more points, and that usually will lead to uncertainty getting better. That may be. It's really kind of a look. This is my theory about statistics. I explained it to Kevin yesterday. I don't even know if he agrees with it or not. But look, mathematics. You have one orange in your left hand, one orange in your right hand. How many oranges do you have? 1 + 1, 2. That's mathematics. And you know what? It describes reality. Statistics, if you ask me, are rules made up by a bunch of people, which it isn't really as based in reality as mathematics or arithmetic. It's just, a standard deviation is what? What does that mean? Uncertainty is this. What does that mean? Well, it means this because, but see, those are things that were made up by people. And so it makes it a lot harder for us engineers to understand because we deal with real physical phenomena. But anyway, so the question is, how is it R squared goes up and the uncertainty is going down or whatever, and well, what should we look at? These are all of these kind of fuzzy things that people have invented. And if you ask me, well, I don't know. It just makes it so it's really unclear of what is real. Kevin, I'm sure you disagree with that. Go ahead and tell them what you think.
No, I think there is something there. I mean, right, statistics, it was the math certainly that I had the most trouble with, maybe because of that. But it does have practical realities. One of the LBL studies looked at, let's calculate what we think the uncertainty is. Let's run the equations, and if we're right, the statistics say that 95 with a 95% confidence interval, that this is the 90% confidence interval. We're 95% sure we're between here and here. So if you do that over and over for these buildings, and you figure out what the actual error is, the actual error should 95% of the time fall in that range. And so they had sort of some test data, and it didn't fall in that range. And so basically they learned that, well, these assumptions and these calculations that we were doing didn't quite work. So it is tied to reality, I think.
Whatever. Yeah, I just like things simple. I'm going to read another one. This says, the more granular, the more change points needed. As Kevin said, if you split things up right. So how is the EDI data from the utility going to include change point data? That is occupancy, unoccupancy, or school or vacation, etc.
Yeah, I don't think it is. I think that's where that's where you're applying. So like in the tool, you would have to set up and you define, it's this period and that period, and you're going to do some, manual tweaking to figure out sort of where your clusters are, which I think is one of the challenges with people that are hoping that they can develop a process that's, say, fully automated and fully repeatable, because it just seems like there's always going to have to be some judgment in it.
There's another thing. This isn't a question. It's something I thought up yesterday. I was going through all these models and for uncertainty, and one thing they don't include is the uncertainty in the data itself. They assume that the data is certain, and that is not true. And interval data often has gaps or just wrong numbers, and that's something I haven't seen that addressed at all. And in fact, that may make interval data a lot less certain than monthly data, which, yes, they maybe have gap. No, I don't know. I just think it's a lot more uncertain. Any comments on that, Kevin?
Not really. I mean, I guess I tend to ignore error, I guess, in a utility meter, but you theoretically are methods, if you wanted to nerd out on it, for, I guess, aggregating the error between your, I guess, the measurement side and then sort of your modeling error. I think I've heard people say, if you think that the error in your metering, say, for example, maybe if you're using a pulse counter, And so there's just an issue with, resolution essentially in that. And so some observations you're a little high and some you're a little bit low because of that. That's one that I guess over time there wouldn't be a bias in it. It would just be a random error. And that might essentially be captured in the error that you're seeing in your model.
Here's one regarding autocorrelation and the comment on lag and gaps. If you have a lag, then the process is no longer linear and more granular in time. And the more granular in time, the greater the consequence of lag on the linear regression, right? What is being developed to accommodate this? That's a good one for you, Kevin, because I don't know that.
I think that's right. I guess there's one issue is, does the model work? Does the model give you a decent prediction? And then the almost a separate issue, I think, is then what is the uncertainty in that prediction? And on the first piece, I'm really not sure how well the models deal with it, or whether the autocorrelation is really a significant issue in in sort of making the model work. Where most of the discussion is around. We do know that autocorrelation throws off the assumptions that we're making when we're trying to do uncertainty, and so that's what people are trying to work on, is just like that uncertainty calc. And that uncertainty calc is something, 99.9% of the option C analysis that's happened in the world has never looked at the uncertainty, but it's starting to get more interest because suddenly, because you've got a state maybe that's looking to do it 10,000 times, and so regulators want to know, when we do all this, how the model's going to give us the savings, but do we know if we can trust it?
Are these regulators statisticians? I mean, how do they even understand what people say when they're talking uncertainty?
Well, I think to some extent, that's why you've got these stakeholder processes and people like Evo, and and I guess the idea is that at the end of the day, hopefully the experts will be able to hash something out and kind of boil it down.
Okay, good. Well, we made through all the questions. Marco, thanks for the hard ones. Oh, wait, got another one. Let's see, what's your experience using coding languages like Python or R and the regression packages within them for this type of analysis? Well, I can give you my experience. We tried to get R working and couldn't. And I think, Kevin, you tried it at your place and you guys ran into problems for like a couple weeks, right? And gave up on it. Is that right?
Well, we're not programmers, basically. I do know, Jesse Smith, that does sort of large scale billing analysis usually for utilities. I know he does stuff in R, and I was kind of amazed how short the program was. I mean, apparently it's very powerful, but again, he's a PhD statistician, and he's not looking usually at doing this like in a rigorous way on a per site basis. It's more like running through 500 participants in some program.
So we tried. There was a program. What was the name of the program in R we were trying to use? Do you know, Kevin? It was like the LBNL model, right? And that's in R.
Yeah, that's right. Yeah, their model is R.
Now we couldn't. Neither of us could get it going. So I mean, look, we're not brilliant, but we're kind of smart. So I assume about as smart as most of the rest of you. So yeah, it's whatever. Anything else? I guess that's it then. Tyler, you want to take over?
Yeah. First, thank you to you both, and thank you to everybody that participated. This was our highest attended webinar since we've been doing these, so I appreciate everybody that hung out. I know we ran late, but that's great. The question email is on the screen, so if you have any additional questions that we missed, send it to that email. We've kept it up there for a while, so yeah, send it that way. And that's it, guys.